Okay, I'm going to have to do this one quickly because Mew is around and she's dying to get her hands on this bagel that I'm about to show you. And she's on the prowl, she's right here. So I want to talk about the four-colour theorem and go away. I want to talk about the four-colour theorem, and the idea is that if you're colouring in a map in your atlas and you want to have two countries next to each other coloured in different colours so that you can easily see where the border is, the question is, how many colours do you need to colour in your whole atlas? And it turns out the answer is 4 colours suffice. And we thought that was probably the case, but we came up with this problem of trying to prove it in 1852. And in 1879, a man called Kemp thought he had a solution. But 11 years later, in 1890, we found a mistake in that proof. And it wasn't until 1989 that we proved it. And we used computers. And it was the first major proof that we used computers with, instead of just doing it by human for the proof, which was massive and controversial. But I want to talk about one of the kind of side cases of it, of colouring in a torus. Now, I apologise for this. This is when I tried making this video about a minute ago, and this thing took a chunk out of it. So, go away. Meow, meow, meow. But it turns out that the four-colour theorem only applies if you're trying to colour in something flat, or if you're trying to colour in something which is topologically a sphere, like if you're colouring the globe, which is the Earth. It maps just to a planar map. Whereas if you lived on a torus, more colours are needed, and it turns out that we need 7 colours to do it. So I spent actually quite a long time trying to colour in this bagel. I messed up the first one, and the idea is we've got these regions. It's like there is one line drawn going around this, spiralling in. So there's a line which goes round here, through the middle, which comes out the other side, and it spirals in, and it keeps spiraling around. And then I've done 7 division lines to cut it. So each of these 7 rectangles has one that it borders on either side, and then it has one that it borders there, one that it borders there, and one that it borders here, one that it borders here, and they're all in that same pattern. I'll put a still up in a minute on this video, which shows you how it's formed. But I think it's interesting that as you change the topological genus of the shape that you're colouring, there is a constant, which is how many colours that you need to do it. And anything that morphs into a torus, topologically, anything which is topologically equivalent, like a teacup with a handle in it, also requires 7 colours if you do it cleverly enough. That's it.